Hello and welcome back to our plasma physics course. This is lecture 25. We're getting really close to the end. I've been saying this for probably about 6 weeks. And we're going to pick up from where we left on lecture 24. If you remember, we talked about the generalized Ohm's law, which had a good number of pretty complicated terms. But in practice, in many cases, if not most, we end up using the simplified Ohm's law under the ideal E plus V cross B or U cross B, depending on how we like to define it. So I'm going to use U to stick with the notation in our textbook. So again, that's the ideal case, or E plus U cross B is equal to eta times J, where eta is going to be the resistivity of the plasma. And maybe I can add the word MHD. So the first Ohm's law is what we use in ideal MHD. The second one is what we use in the resistive MHD. And as the textbook emphasizes, the resistive MHD Ohm's law is not necessarily wonderfully accurate description of the physics in our plasma, but it's the simplest way we can include resistivity in our description. Again, the reason why this is used a lot is not because it's good, but it's because it's simple. And it's not terribly bad, or we wouldn't be using it. And this is all, unfortunately, we have time for in talking about the Ohm's law. Of course, there could be more to say. Well, we're going to use our Ohm's law again in a moment and say something more. Now, I'm going to give up on my hope to draw a straight line here. I'm going to add something on what many call the equation state. And as you'll remember, I called closure for the reasons we have discussed during this course. We've already encountered this. The simplest isotropic single fluid closure we can write looks like this. P over rho subscript m, so that's the mass density, to the gamma does not depend on time. So let me make some space here. I did say that out loud, but let me also write it. That eta here is the resistivity, which is the inverse of the conductivity, or 1 over sigma, which is what we had in a previous lecture. Now, this is not single option for the closure, really. I will say this is a family of closures. And in fact, what happens is that what is called the polytropic index gamma can assume different values. And depending on the value that we take for gamma, we're going to have a different closure, but with some similarities among closures with the same value for gamma. And I don't know if it's worth spending much more time on this, but if we set gamma equal to 5/3, that will be our isentropic closure. If we set gamma equal to 1, that will be an isothermal closure. Isothermal because the temperature of the plasma is not going to depend on time. P over rho, or P over N for number density, is proportional to the plasma temperature. Another option is gamma going to infinity. And remember, I don't like writing gamma equal to infinity because infinity is not a number. But this will be the incompressible closure, where density is not allowed to change. And you can also take this last one is really not used. I will set it as a curiosity, but in principle, you could take gamma equal 0, and then what you have is that the pressure is constant in time. But again, I don't think that this is used anywhere in plasma. There will be constant pressure or isobaric. But as far as I'm concerned, we could pretty much forget about this one. The next step in our discussion is the case where the system is not simple isotropic ideal MHD. And what we're going to give up is, or relax, is the isotropic assumption. We're still assuming an ideal system. But the pressure now is going to be a tensor rather than a scalar. And therefore, we're going to need more than one closure. Remember what happens with the the closures we just discussed, the polytropic closures, is that we need to specify a relation or an equation relating pressure and density, because otherwise we'd have more unknowns that we have equations. If we have more than one component of the pressure, we need an equation for each additional equation for each additional component of the pressure. And the case that's used more often when we assume anisotropy in the plasma is the case where we only set two different pressures, a parallel pressure and a perpendicular pressure, where parallel and perpendicular refer to the direction of the magnetic field. Here is how it goes. Oops. So let's assume that the magnetic field is in the z direction. And that pressure parallel to the magnetic field or perpendicular to the magnetic field have different values. Or at least they're allowed to have different values. That will give us a pressure tensor that looks like this. We're going to have a P perpendicular in the XX component, a P perpendicular in the YY component, and a P parallel in the ZZ component, and everything else is zero. Not going to have cross terms. Then one way to close the system is the well-known CGL closure, or well, closures, I guess, since we have two, where C, G, and L are the names of the three physicists that introduced this model in the 60s. Chu, Gold, Berger, and Low. Okay, the two equations that we need to close the system look like this. One, that the time derivative of P perp, let me make this line straight, over mass density times B is 0. That is, the quantity inside the brackets is conserved. And the second one is that the derivative of, now we have p perp squared times p parallel divided by rho m to the 5th power is equal to 0. That's, I'm sure, super intuitive. You can all see where that comes from. In fact, as our textbook reminds us of, these come from conservation of the first two adiabatic invariants. And unfortunately, we don't have time to get into much more detail about this, but if you ever run into an isotropic fluid model for plasmas, chances are this is going to be the model you train the CGL model. Okay, but before we move to anything else, I will just mention that the second closure equation is often written in a different way. You can see that I can write P per square P parallel over rho to the 5th as P per square over rho square times P parallel over rho to the 3rd power. But from the first closure, I get that P per over rho times B is a constant. Let me call it C1. And therefore, P perp square over rho square times 1 over B square is equal to a constant. Square doesn't matter, or P perp square over rho square is equal to a constant times B square, which I can replace in the equation above to obtain that P parallel times B square over rho to the 3rd power is a constant, or that the derivative with respect to time of P parallel B square over rho cube is equal to 0. And that is another form of the same closure. It's the one I've encountered more often, but it's going to depend on circumstances. You may find one or the other. But the last two squared equations are the same equation. The reason I think why it may be preferred to write it in the second way is that in that expression you have explicitly an expression that only involves the perpendicular pressure and an expression that only involves the parallel pressure. Now, still speaking of pressure, let me make a little division here. Another useful concept in fluid model is what is called magnetic pressure. And here I'm going to be talking about ideal MHD. And therefore, the pressure is a scalar field. And let's see where that comes from. The idea is that we can write J cross B as using Maxwell's equation, so 1 over mu naught del cross B, and then you go dig into vector identities, for instance, the plasma formulary, and you'll find that the gradient of A dot B is going to be equal to A dot grad B plus A cross del cross B plus B dot grad A plus last term B cross del cross A. From which with A equal B, you obtain that the gradient of B dot B, which is just B squared, is equal to B dot grad B plus B cross del cross B plus B dot grad B. Okay, so that's the same term as here, just put a 2 plus B cross del cross B again. So I'll put a 2 here too. Reordering terms, we get that del cross B cross B, divide everything by 2, is equal to B dot grad B minus the gradient of B squared over 2. Or that J cross B, bringing in the mu naught, is equal to 1 over mu naught B dot grad B minus the gradient of B squared over 2 mu naught. Okay, this can actually be written as a tensor. I don't think that's terribly useful. In general, if you're using this form, if you're using ideal MHD, then pressure is a scalar. There is not much to be gained by using tensor notation. But going back to the momentum equation, we see that we can combine here, use this momentum equation, we can combine the gradient of the pressure with the gradient of b squared over 2 mu naught, and write that density times du dt is going to be equal to 1 over mu naught b dot grad b minus the gradient of p plus b squared over 2 mu naught. Which is another way to write the momentum equation. And this last term here is what we call the magnetic pressure. Maybe I can square this equation. Writing the momentum equation this way actually also allows you to naturally introduce another quantity. The Greek letter beta, this could be a B, let me try again. Which is the pressure divided by b squared over 2 mu naught. This is a definition, and this is equal to obviously 2 mu naught p over b squared. And that is a quantity that we find in plasma physics all the time, and that's going to tell us whether the pressure forces are larger or smaller than the magnetic pressure forces, which one is dominating. And let me make it clear that this is the lowercase Greek letter beta. I don't know who named it that way and why and when, but everybody in plasma physics will recognize that quantity. In this can be larger than 1 in astrophysical systems, at least in some places. In fusion experiments, it's typically less than 1 or much less than 1. And it would be nice to be able to build a fusion reactor where data can be rather larger than one, because then it will be less expensive to build the magnets for the same amount of power. We're almost done with the general discussion of the MHD model. The next, we're obviously closely following the textbook here. The next thing we should talk about is the convection and diffusion of the magnetic field. Now, this is going to be important in various places. One place where this matters is magnetic reconnection, which is going to be important in fusion experiments. It's going to be important in the magnetosphere. It's going to be important in solar physics. And this will also come up quite a bit in the solar physics without the reconnection part. And as we'll see, the diffusion process of the magnetic field sets some time scale, which is what we call the resistive time scale of our system. That is going to tell us whether resistivity is or is not important for the systems we're looking at. If we're looking at processes that occur on time scales that are much faster than the resistive time scale, we can most often ignore resistivity, set it equal to 0. On the other hand, if the opposite is true, then resistivity needs to be kept in our description of the plasma. Okay, now just follow what our textbook does and eliminate J, the current density between Ampere's law and Ohm's law, and obtain that del cross B is equal to mu naught sigma E plus U cross B. And then I'm going to take the curl of this equation. I should have left myself a little bit more space. Well, let me do it this way. I'm going to take the curl and use the expression, the vector identity that we've used before, that del cross B is equal, actually it's not the one we used before. Take it back, different one. It's gradient of divergence of B minus del square B. Of course, del square B is 0. And del cross E we can get from Faraday's law. And this will give us minus dB over dt. So we'll have, let me just set this to 0. I have minus del square B is equal to mu naught sigma minus dB over dt plus del cross U cross B. Let's maybe make these square brackets. Oops. Sorry about that. And rearrange terms and keep the time derivative on the left-hand side. This gives us dB over dt equal to del cross U cross B plus 1 over mu naught sigma del square B. This is sometimes called the induction equation for the magnetic field. If you have any familiarity with fluid dynamics, which you may or may not have, this is clearly diffusion equation. More precisely, the second term on the right-hand side, the square B is a diffusion operator, while the first term is represents the convection of the magnetic field, how the magnetic field is transported by the plasma, and the diffusion term represent how the magnetic field can diffuse across the plasma if the conductivity went to infinity, or the resistivity went to 0, which is the inverse of the conductivity. You could neglect the last term, and all you will have in your system will be advection or convection of the magnetic field. On the other hand, if the resistivity, the process is dominated by the resistivity, then you will neglect the curl of U cross B. Before we go any further, I will point out that this is a place where, especially when we deal with magnetic reconnection and tethering modes, we see the occurrence of what is called, where is this? Well, okay, so the resistivity can introduce what is called singular perturbation. The idea is that I have a differential equation for the behavior of the magnetic field. If the resistivity is 0, that differential equation has first derivatives with respect to space of the magnetic field that comes from the curl, if the resistivity is not exactly zero, I'm going to have second derivatives of the magnetic field, which means that the order of my differential equation changes from first to second. That's what makes the perturbation singular. By making a quantity infinitesimally small, but not exactly zero, I get a completely different set of solutions, because I'm going to have solutions to a second order equation instead of a first order equation. Now, an intuitive or a convenient way to understand or decide whether resistivity effects are important in our system is to define dimensionless number as the curl of U cross B I'm going to take the norm of this because I'm going to need a scalar quantity divided by 1 over mu naught sigma times del square B, again taking the norm of this quantity. All I've done obviously is take the ratio of the two terms on the right hand side. And what we normally do is to try to estimate the numerical value of this number by setting the nabla symbol, so gradient or curl or the square or anything, to be proportional to 1 over L, where L is some characteristic scale length. For either my system or my problem. And if we do that, we can estimate the number that we have up here as, oops, sorry. To be of the order of 1 over L. For the velocity, I'm just going to leave the norm of U times the norm of B. I'm getting rid of the vector symbols to indicate that these are norms, divided by 1 over mu naught sigma times B over L square. That's a sigma, not an L. Sorry about that. Now I can, of course, get rid of B. So perhaps surprisingly, or maybe obviously, this does not depend on the scale of B. And I take mu naught sigma L to the numerator, divide by U. Let's see if I lost anything along the way. Yes, I'm not dividing by U, I'm multiplying by U. Sorry. What am I doing? Okay. Let's make it a little more u naught sigma L squared divided by L. I just have one L left and U was in the numerator. Now this quantity is going to tell me if the convection or the diffusion term is more important. And this is what is called the magnetic Reynolds number. And this is typically, well, not always, but it's often indicated in different ways. Let me just move this so that it is visible better. There, better. In some cases, we see that instead of using the magnetic Reynolds number, we use what is called the Lundquist number, which is basically the inverse of the Reynolds number. And let me put that in writing. This is the inverse of the magnetic Reynolds number. I should have mentioned that the magnetic Reynolds number is called magnetic Reynolds number because it's similar to the fluid Reynolds number, the original Reynolds number that will give you the ratio between inertial effects and viscosity effects. So if we interpret plasma resistivity as some type of viscosity or some type of dissipative effect, it may make sense to call those two numbers with the same name. Now, the Lundquist number is usually indicated with capital letter S, and that's going to be the inverse of the magnetic Reynolds number. And this is typically large. In fact, in both laboratory and astrophysics, whereby astrophysics, space physics, solar physics, this is in general a large number. Unless the plasma is really special, the resistivity of the plasma is negligible. The way it is maybe a little confusing is that we don't necessarily know if, so we assume the conductivity to be large, and it may not be obvious if the product between the conductivity and mu naught, which is a small number, gives us a large number. And I just realized, sorry, I completely messed this up. I was thinking of something else, and instead of defining the Lundquist number, which is the same as the magnetic Reynolds number, but people do all sorts of things, but usually the Lundquist number is defined using the event velocity. And that will still give you a fairly straightforward way to figure out if the resistivity is important or not in your system. I don't want to give any specific numbers because those are going to depend on what precisely you're looking at. But in magnetic confinement fusion, it's pretty standard to see numbers like 10 to the 6, 10 to the 9. In some astrophysics, you can see even larger numbers. And maybe some cold plasmas and some other circumstances that this can be lower of the order of 10 to the 2, 10 to the 3, but still typically pretty much larger than 1. Now we can close this part. I'm going to give you just one more brief discussion of something else. Something that is called the frozen-in law, which is nothing else than conservation of magnetic flux. And our textbook defines it and proves it in a couple of different ways. I'm going to keep it brief and simple to cut a long story short. I'm going to pick an arbitrary surface in my plasma, and I'm going to calculate the integral over that surface, or B dot ds. That's the flux of the magnetic field. Across that surface. And I'm going to call this quantity psi, as we have done in other points of this course, that's the fusion name for the magnetic flux. Okay, then I'm going to ask the question, what is the time variation of that magnetic flux? Well, that's going to be the time variation of this integral, which, as you all know, is going to be given by the partial derivative of b with respect to t dotted with ds and integrated over the surface, plus the essentially this change in the surface, which we can write as u. I will use lowercase u for now. Crossed with the vector in the direction of b dot dl. Oops, sorry. I made a bit of logic leap. Okay, sorry, I got two different proofs that proceed in different ways mixed up, and I use the unit vector instead of the actual vector. So I think more carefully about what I'm saying. Okay, I wanted to emphasize that u is the velocity of the surface, and that in fact we can write this second term in a different way. This equivalent is not the next step. Okay, integral of partial of b with respect to t dot ds plus the integral of b dot derivative of delta s in dt. So how the surface is changing over time. And if you just make little plot of this, you can convince yourself that the differential, I'm cutting this short because of time constraints. Okay, differential of this surface is going to be given by u dt cross dl, or call it delta L, since I'm using bigger uppercase delta. And then if I take the derivative with respect to time, I obtain that the derivative of my surface over time is going to be equal to u cross dl or delta L if you prefer. Okay, almost there. Now I'm going to assume that my plasma is ideal. And I'm going to consider a surface that moves with the plasma. That is, I'm going to identify the velocity u with the velocity of the plasma. Then I obtain that deep psi dt is going to be equal, dB over dt is just u cross b, because I'm ignoring the resistivity. And I'm going to use Stokes' theorem and turn this into u cross b dot dl. And the other piece is going to give me the integral of b dot u cross dl. And we're done because these are equal and opposite. In other words, the magnetic flux, what we've just proven is that the magnetic flux through an area that is bounded by a closed contour that is painted on the plasma, that is a closed contour that is moving with the plasma, does not change if the plasma moves. And again, this is going to be true if we can neglect resistivity in the system. Okay, so that's going to be it for this lecture, and we'll see you back for lecture 26.